This talk is by Daniel Escudero on efficient protocols for Oblivious linear function evaluation from Ring-LWE.
Okay, great, Peter. Thank you very much for the introduction. So as Peter said, this is about protocols for OLE based on the Ring-LWE assumption. And this is joint work with Carsten Baum and Peter Scholl from Aarhus University, Alberto from Universidad de Vigo, and Juan Ramon from EPFL in Switzerland. Okay, so let me begin with a very quick introduction. So what is OLE to begin with? So OLE is this functionality, this two-party functionality that proceeds as follows. So you have Alice with an input V and Bob with an input U. And what the functionality is going to do is that it's going to send a completely random value to Alice, alpha, and it's going to send to Bob beta that is defined as U times V minus alpha. So overall, the addition of the two values, if you sum alpha plus beta, that's going to give you U times V. So this functionality is essentially turning like inputs into shares of the product of the two inputs. I want to say something that is, you probably have seen this functionality before in a different form. Alice has an input, Bob has a function, and what Alice gets is like the evaluation of her input on Bob's linear function. Well, these two are actually equivalent, and since this is the one that we instantiate, this is the one I would rather focus on. So why would you study OLE? Well, OLE has many applications. You probably have seen some of them like along the conference itself. So for MPC, for example, which is of course our case of interest, we can use it to generate multiplication triples, for instance, and more generally, you can use it to handle multiplication of shared values. It's like a very fundamental primitive for MPC. It can also be used in other domains like PSI and like many other cryptographic constructions. So in general, if you improve the efficiency of an OLE protocol, in principle, you are improving the efficiency of a lot of different protocols. So it makes sense to, it definitely makes sense to work hard on improving this primitive. Okay. So let me begin with some introduction, with some notation, because I want to be as lightweight as possible, but I still have to introduce something. So M is the modulus for the OLE, so the expression I described before, the equation alpha plus beta equal to U times V, that happens modulo something. So this something is going to be M. And we're going to have two integers, Q and P, Q being larger than P, which is larger than M, where M divides P and P divides Q, sorry. And this is just some parameters for the encryption scheme that we're going to use in a moment. We also have the ring, the polynomial ring modulo x to the n plus 1, where n is a power of 2. This is widely used in lattice-based cryptography. And the cool thing is that by choosing the parameters in a certain way, this ring, like each polynomial in this ring has degree, of course, at most n. But it turns out that by using certain special representation.
My phone, if that's okay, and listen to the other.
Oh, Jack, I think you're unmuted. All right. So. Okay, so then every like a polynomial in this ring using certain special representation corresponds to a vector of n integers, and multiplication of two polynomials corresponds to pointwise multiplication of these vectors. So basically, one OLE relation in the ring corresponds to many OLE relations over the integers. Okay, what else? What another notation we have is that for an integer in ZQ, we can define the rounding towards P by just P divided by Q times X, and then round it as a real value. So you can think of this as just, you take a value in ZQ, you scale it down to ZP, you scale the integer ZQ to ZP, and then you round to the nearest. Okay, and we extend the definition to polynomials because you can just apply it like coordinate, to each component, to each coordinate of the polynomial. Then finally, we have two distributions that will be bounded. You don't need to think about so much about them, but they are like just two bounded distributions that we're gonna draw some values from in a moment. Okay, so something important here. LPR encryption, right, by Lyuboshevsky, Picard, and Regev, 2010. So this is a simplified version of it, and it's going to be like at the core of our technique. So I want to make sure like I get the idea across. So first, the public key is generated as follows. You can choose part of the public key, which is this A input. You can choose it, which is important, as we will see in a moment. And the way that you generate the other part of the public key B is by sampling the secret key S and just defining B to be A times S plus E. Okay, so think of B as A times S essentially, but it has like a small error added to it. E is supposed to be small. And to encrypt, you take the input X and you compute these two numbers, C1 and C0, these two polynomials, sorry. C1 is defined as minus 8W plus E1, where W and E1 are drawn from the error distribution. And then C0 is defined as BW plus E0 plus the scaled version of X. So Q divided by P times X. Remember that P divides Q, so this is an expression that makes sense. And to decrypt, you just take an appropriate linear combination of these two, C0 and C1. You take C0 and you add S times C1. And it turns out that if you do this and then you round mod P, then you actually get back the plain text X. And because it will be important later on, I want to very, very quickly give the idea about why is that the decryption works. These techniques will be important later on. So I just want to convince you that that's the case. If you take this linear combination, C0 plus SC1, and then you round to P, then after you do the math, you end up with this rounding of X plus P divided by Q times some error, some E prime. Because X is an integer, it can actually go out of the rounding. And once something goes out of the rounding, what remains, this thing should be small, P divided by Q times E prime should be small, and that should give you essentially X. When I write approximately equal to X, I don't mean like it's close, but I actually mean that most of the time is gonna be the same. And we just choose the parameter so that P divided by Q times E prime is small enough, and that's very easy to do. E prime is essentially less than Q divided by P times divided by 2, I think. So far so good. That's why decryption works. And we also need this other important property of this encryption scheme. And usually when you encrypt something, like you shouldn't need the secret key at all. And with this type of encryption, you can actually encrypt, you can actually obtain an encryption of any plain text you want times the secret key without ever knowing the secret key. And the way that it works is as follows. You define C1 and C0 in a very similar way as we did it before. I won't go back, but like the two are very related, except that this time you are adding Q divided by P times X. You are adding it to C1 and not to C0. Because if you remember, the way that we decrypt is by taking a linear combination where we multiply S to C1. When we decrypt this thing, you're going to multiply S to X, actually, and that's why you get an encryption of S times X. A very important property that we're going to use in a moment. Okay, so our starting point is this observation of Boyle et al. In Eurocrypt 2019 that says the following. So if you have x1 plus x2 that are random values, such that when you add them, you get Q divided by P times X plus some small error. So think of this as additive shares of Q divided by P times X. So I think Alice has x1, Bob has x2, and they have shares of this value. But they are like a bit noisy. So they are not quite shares of Q divided by P times X, but shares of that plus E. If you have that, and if each party, Alice and Bob, if each party rounds their share locally towards P, so that's what the equation is saying, x1 rounded to P and x2 rounded to P, and you add these two shares together, you actually end up with shares of X. And the reason why this holds, again, I don't want you to focus too much on this equation, but the idea is that if you round P, if you round x1, sorry, then again, X is going to go out of the rounding because it becomes an integer, and then you get this other noisy share, which is P divided by Q times E minus the actual share that Alice or the other party is supposed to hold. But this thing will be small, and like we're going to choose the parameters so that this summand here is small enough so that it doesn't actually affect the rounding, and what this ends you up with is X minus the share x2 rounded to P. And I want you to notice that this is a different type of small than the other one. Like the previous one is just E needs to be less than Q divided by P times 2. That's fine. But this one, you actually need the gap between P and Q to be super polynomial, and that's how we choose our parameters. Okay, that was the first observation. What is the second observation? Well, it all stems from the fact that decryption is linear. So if you have an encryption, C0 and C1, of some value X, and suppose that Alice and Bob, they have additive shares of the secret key, then, because, I mean, we can technically, let's say, run the decryption circuit in MPC. But in this case, it's super simple, actually, because you just do C0 plus S times C1, that's the linear combination you do to decrypt. Because the shares are linear, this is going to be C0 plus S times C1, all in shares. By the way, that's when I write like the angle brackets, I mean secret shares. And then this is going to be more or less Q divided by P times X, which is I say more or less because this is going to be noisy. There's going to be like an error term added to this expression. But this is fine because from the previous observation, the one that I showed in the previous slide, if each party rounds its share of this value locally, that's what I mean when I write a rounding of an angle bracket of a sharing. If each party rounds locally, then they end up with shares of X. That's what the previous observation told us. If you have noisy shares of something, Q divided by P times something, you get shares of that something after you round. So that's pretty cool. You can essentially run the decryption circuit in MPC and get shares of the plaintext. That's the first observation. The second observation, of course, is that you can do the same with a KDM encryption because a KDM encryption is just an encryption, but of the plaintext times the secret key. Applying the same trick will give you shares of the plaintext times the secret key. So far, so good. This is the most interesting part, I think. So if you have an encryption of another potentially unrelated value y, and you do this linear combination, x times d0 plus xs times d1, where you have shares of x and shares of x times s from the previous two steps, then if you do the math, this actually will lead you to shares of x times q divided by p times y. And we can, yet again, applying this trick of locally rounding. And if you do that, if you locally round, if each party locally rounds its own share to mod p, then they will end up with shares of the product between x and y. So what do we do here? If you look from top to bottom, you begin with just an encryption of x, an encryption of y, and you end up with shares of the product. And if you remember, that's what OLE wants us to do. You want to get you want to begin with two inputs and then get shares of the product of two inputs. So this is essentially like a template to get this kind of primitives. Just one thing, so this is the starting point, but there are many points for optimization, and this is essentially like our main contribution. We take this template and we optimize it explicitly and specifically for the case of Oblivious linear evaluation. I want to stress that the work of Boyle et al. Is more general, it's homomorphic secret sharing, and like it can be, it's a bit more general than OLE. So in our case, you can actually start optimizing many things. Like for instance, just to point out something, the shares of X that you get in the first two lines, I mean, you don't actually need them because X is going to be the input of one party. So therefore, by default, you kind of already have additive shares because one party can define the share to be the value and the other party can define the share to be 0. So you can apply many optimizations like that, and then that's essentially what our protocols we do. So with that, let me begin with our first protocol, which we call PKI-based OLE protocol because it's based on a public key infrastructure. More precisely, our first protocol assumes that Alice and Bob have essentially a secret and public key pair each. So Alice has SA and BA, that is A times SA plus an error. And Bob has also SB, comma BB. And notice that both of them use the same A, and that's important, but that's fine because if you recall, our generation procedure allows you to input A as a parameter. Okay, so if you have this public key infrastructure, you can always define this B to be the sum of the two Bs, and S to be defined as the sum of the two S's. And then A comma B becomes a public key such that the secret key is the sum of the two S's. So the secret key is going to be secret shared among the two parties, which is great because that's kind of the starting point of the first observation we discussed before. So with this starting point, the protocol proceeds as follows. So on the left, we have Alice. She has an input V that is a vector of polynomials. That's why it's in Rm to the n. So it's a vector of n polynomials. This is because our implementation is actually like our protocol is actually vectorized. It can work on many values at once. So Bob also has a vector of a lot of elements or a lot of ring elements. And the first thing that will happen is that Bob will send to Alice a KDM encryption of its own input U. Whenever I write KDM encryption of a vector, I mean like encryption of each one of the coordinates. And then Alice receives this value, and each of the parties can compute these intermediate shares, rho Alice, that is the rounding of S Alice times C1, and rho Bob, that is the rounding of C0 plus S Bob times C1. So I don't want you to focus on the detail, but the idea here is that this is the first step on the main observation we discussed before. This is like the run the decryption circuit in MPC kind of step. So after this step, you get shares, row Alice and row Bob, of S times U. Okay. For the second step, Alice will send to Bob an encryption of her input V under different parameters. Notice that the first one is P and Q, the second one is M and P. They are going to be smaller. So she sends an encryption of her input V, D0, D1 to Bob. And once this is Bob receives this, they can define the final output, which is Alice defines alpha, the rounding of D1 times row Alice towards M. When I write star, by the way, I mean coordinate-wise product, because these are two vectors. Bob outputs beta, that is just D0 times U plus D1 times row Bob, rounded towards M. And again, this is the second part of the observation at a very high level. This is running the decryption circuit in MPC again. And this will lead the parties with shares of U times B. Alpha plus beta will be equal to U times B mod M, which is essentially what the OLE relation wanted us to achieve. So this is our first construction for OLE. I just want you to notice that the protocol is conceptually very simple. And something that is also very important about this protocol that I want to emphasize here is that it looks like two rounds. Bob sends a message to Alice, Alice sends a message to Bob. But it's actually one round, because the message that Alice sends back to Bob is not dependent on the first message that Bob sent to Alice. It's just an encryption of Alice's input. She can send it anytime she wants. So this actually happens in one single round. And the way that this will operate is that at the beginning of the protocol, each party will work locally on computing what they need to send. And then whenever they have it ready, they just send it. So it's a one-round protocol, which is very good for high latency networks. Another thing I want to say about this protocol, by the way, is active security doesn't come for free. Like, there are many attack vectors here. This is all passively secure so far. One attack vector, for example, is the following. Bob's input is supposed to be a vector of polynomials modulo M, but the encryption scheme that Bob is going to use actually allows him to encrypt elements that are mod P, that is potentially much larger than M. So he can just not encrypt something mod M, encrypt something mod P that is larger, and then perhaps learn something by doing that. And in fact, you can show that that's the case. If Bob does this kind of attacks, then he can learn information about Alice's input. So to fix this, you can actually use generic zero knowledge proofs. For example, the proofs by Baum et al. Crypto 18, sorry. They allow you to prove these kind of statements, the one that arise from this, and this is what we do in our work. Okay, so let's actually optimize this protocol. I'm going to show you the second protocol we propose, which is a secret key based protocol, and you see why in a moment. The main observation is the following, that we can optimize the protocol if instead of using the public key variant of LPR that I described at the beginning, we use the secret key variant. What do I mean by secret key variant? Well, like you can similarly to the way we define the public key encryption scheme, there is a secret key encryption scheme that uses only one ring element, but at the expense, of course, not being public anymore. So you need the secret key to encrypt and decrypt as well. If you modify the protocol so that you use the secret key variant, then everything becomes more efficient, but unfortunately the setup is more involved. It's not a PKI anymore, which is a very natural assumption. Now it's like more complicated. So the setup will be the following. Alice will receive a pair, SA and sigma A. Both will receive SB and sigma B, where sigma B is defined as the product of the S's minus sigma A. So effectively, sigma A and sigma B, if you sum them up, they are the product of SA times SB. So this looks like some kind of OLE, but unfortunately, it's not quite that, because SA and SB, they are supposed to be secret keys. So this is not exactly OLE, because they have to be drawn from a special distribution, not from a uniform distribution. But anyway, it's just a one-time thing. Like you just do it once, and then you're gonna get many OLEs out of it, as I'm going to show in a moment. With this setup, and yeah, we also assume that Alice and Bob, they have access to uniformly random A and A prime. This is going to be used for the encryption of their inputs, as we'll see in a moment. And this, we don't really count the complexity of this, because this can be sampled from anywhere. This is just like a public random value that is a public random value. So what is the protocol now with this new setup? So Alice has again an input V, Bob has an input U. And what Bob does is that it sends this value to Alice. It's only one ring element, or sorry, I mean like one vector of ring elements. And it's Q divided by P times U plus this term that is supposed to be masking exactly Q divided by P times U. And I didn't write it like that, but this is essentially a secret key LPR encryption of Bob's input. So this is what Bob sent to Alice. And once they receive this, Alice can define the partial share or the intermediate share rho Alice to be S Alice times C minus A times sigma Alice. And Bob can also define this rho Bob to be minus the rounding of A times sigma Bob. Again, like this is maybe like it doesn't provide so much insight what this equation is, but this is essentially running the decryption circuit in MPC. I think that's the best way of seeing it. And then again, like before, like now they have additive shares of S Alice times U. And in the next step, Alice will send an encryption of her input. This is what this expression is, an encryption of her input V to Bob. And once Bob receives this, they can define the outputs to be minus the rounding of A prime times rho Alice, that's the share alpha, and the share beta is the rounding of U times D minus A prime times rho Bob. And if you do that, then again, you can see that alpha plus beta is going to be U times V mod M, which is great. It's the only relation we wanted in the beginning. So observation about this, have the communication complexity because we're sending one ring element, like each party is sending one ring element. Again, I mean like one vector of ring elements. Instead of two, as like before, and Alice, again, like, is just sending only one. The same pattern is only one round, like the two messages are independent, so they can be sent simultaneously. For active security, we unfortunately get the same attack vector as I described before. So to actually make this actively secure, they have to prove in zero knowledge that what they send is correct. And unfortunately, in this case, you cannot just take zero knowledge techniques out there because the type of statements that arise in the setting are different. So for this, we actually introduce new zero knowledge arguments with good amortized complexity for proving the well-formedness of secret key LPR ciphertext, which is the type of statements that we get here. I won't go into the details of this. I invite you to see the paper that hopefully will be in ePrint like in a couple of weeks from now. And yeah, again, like this is, we use existing techniques though, but it's not a standard zero knowledge argument you can find out in the literature. Okay, the final things I want to talk about is performance. So first, let me give you a few words about communication complexity. So I have this big table that I want to help you digest. In the left side, we have several protocols. The first two are our protocols, the public key variant and the secret key variant. And the next three are additively homomorphic encryption-based protocols, where one party sends an additively homomorphic encryption of the input. The other party multiplies the value, adds a random value to it, and sends the result back to the first party so that the first party can decrypt. Somewhat homomorphic encryption is similar, except that you multiply two ciphertext. So you need a homomorphic encryption scheme that supports one multiplication. And Ritz-Solomon encodings, which are like based on the work of Ghosh et al. In Eurocrypt 2018, I think, or 19, sorry, I cannot remember it exactly. And the distinguishing factor of our protocols, the first thing I want you to observe is that our protocols are the only ones with only one round of interaction, which is very important that you have a high latency network. And secondly, our secret key OLE protocol is the one with the lowest communication count. And I think this is a very appealing observation if you want to have a passively secure protocol or even an actively secure protocol that is like reasonably efficient. Our secret key variant will be like a reasonable option, in my opinion. Okay, this is communication count. And now I want to talk a little bit about performance, like actual timings. So we implemented our protocols. We don't have any communication. This is all like just computation, which in lattice-based cryptography is, if you have a very, very fast network, it's usually the bottleneck. And then I want to tell you what the parameters are. We have a small n, which is the length of the vectors, to be 128, big N to be essentially 16,000. If you multiply these two, which is the total number of OLEs you get essentially 2 million. So this number for 2 million. And I want you to focus on this big table has a lot of numbers. I just want you to look at this. So M, for a modulus M that is essentially 60 bits long and 159 bits of security, it takes Alice to handle the first message that she receives from Bob, essentially half a second, 564 milliseconds. And it takes Bob to prepare this message essentially 1 second. So this is like very fast if you take into account that we're talking about like 2 million OLEs. And in the second message is essentially half the cost of that. It takes Alice half a second to process the message she needs to send to Bob, and it takes Bob a quarter of a second to process that message. And I know this can be confusing, so I actually prepared like a diagram for you to take this into account with what I will expect will be like this, how this will behave in an actual network. So in an actual scenario with a 600 Mbps network, this is all extrapolated, by the way, I didn't run this, the execution will look like this. So at the beginning of the computation, it will take 350 milliseconds for Alice to compute D, and it will take 462 milliseconds for Bob to compute C. Then they send the messages, again, once they have them. And this is my calculation based on the network speed about like for the time that it will take for these messages to arrive. And then Bob can compute raw Bob immediately after sending C, but Alice has to wait to receive C because raw Alice depends on C. So that's how the communication looks so far. And then in the final step, each party can compute the final share. And this is how the timing will look like. So overall, the communication will be essentially 2 seconds. So from beginning to end, it will be 2 seconds to process 2 million OLEs, which I think is very competitive. By the way, these numbers are extrapolated. This is going to be different in real life, but this should give you an indication of how well this performs. And of course, for reference, this may not be so clear. So for reference, we also implemented the somewhat homomorphic encryption-based one. And if you look at the bold numbers, we see that Alice's time just alone is already 1.5 seconds. And Bob's time is going to be 1 second. And they have to be sequential because you have to send and then the other party has to process and then send back. So at least without communication into account, this is going to take you 2.5 seconds. So this doesn't sound like very competitive with respect to our protocol. With that, I would like to conclude. And if you have any question I can help you with, of course, I will be happy to do so.